Hello, here we are with a 2018 Oxford Pat. So anything changed? Right, we're all in one section again, like we were last time with a 2017. Oh, we've now got calculators are allowed. So we've got no tables or formula sheets. I mean, I doubt if anyone's turning up with them anyway, turning up with their book of log tables. But yeah, we can have calculators, answers given exactly or simplest terms. We've got multiple choice. And then, oh, you can get partial credit for your multiple choice working. G is 10. Right, fine, here we go. So I'll go through the multiple choice ones and probably stop after those, I would imagine. So what's the next number in this sequence? 4, 5, 9, 14, 23. Gaps of 1, 4, 5, 9. Oh, right, okay. So yeah, the gaps, we got Fibonacci, haven't we? So we're doing 4 plus 5 is 9. 5 plus 9 is 14, 9 plus 14 is 23, so 14 plus 23 is 37, so we've got C. So, yeah, we can, maybe you should be writing some of these things down then, if they're giving you working. So, yeah, let's put those down, etc. Question 2, which of the curves shown in the figure is not a trajectory in the gravitational field of a central star at 0, 0, marked by the star symbol? All right, yeah, they put a star here. So which one of these, or more than one? They got more than one or our options? So all of them, none of them, just 5, 4 and 5, or just 3? Right, so yeah, we got various options. Well, all of these orbits have got to be conic sections. So as in they've got to be circles, ellipses, parabolas and hyperbolas. So we need to have that. So they're conic sections with star at focus. So we have to have that as well. So let's see what we got on these. So for 1, that's great. We got an ellipse with the star at one focus. For 2, we got a circle with a star at one focus. For 3, we've got a circle with the star just in the middle of nowhere. Then we've got 4 looks like a parabola with star at focus, and then 5 looks like hyperbola with star at focus. So yeah, we're saying just 3 is not, which is E. Excellent, excellent. Which combination of units is the odd one out? Right, this will be fun, won't it? Oh, they got some weird ones here as well. They brought Teslas in. Right, okay, so yeah, they're really pushing people on this. Right, so a volt is a joule per coulomb. So here like, we got coulombs times joules per coulomb per meter. So we've got joules per meter. Well, I mean, that's force, isn't it? Because work done, joules, is force times distance. So that's newtons we're in here. Oh, it's also the same as D. So A and D can't be odd ones out because they're the same as each other. That's newtons as well. So we're going to have other newtons kicking around here. So Tesla, that's magnetic field strength. So we've got force equals BIL. So if we've got Tesla times the, oh yeah, this is it. This is BIL. That's B, that's I, that's L. So that's newtons, so it's not B. Then what else have we got? Oh, that's mass times acceleration, so that's newtons. And then we've got whatever this thing is, which is charge times velocity. So because we've got F equals BQV, so charge times velocity is that. So this is F over B. So E is the odd one out there. That's quite a tough bunch because you're not used to just looking at them. I know we do unit analysis, but we're not used to looking at that as being a set of units that go together. So trying to translate these across to being equations. Yeah, that's an interesting question. That's quite difficult. Right, 90 people enter a maze. At each junction, a third will go left, 2/3 will go right. After 3 such junctions, what is the most likely combination of turns people would have taken? So after 3 junctions, we either got left, 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 right, left, right, left, right, left, left, right, right, left, right, left, right, or left, right, right, or right, right, right. So the most likely ones, well, it can't be that because right, right, right is more likely, and it can't be these. So for this, that's going to be, so it was 2/3, so that's going to be 8/27 to go right, right, right. But then going this way, we're going to have 2/3 times 2/3 times 1/3, so that'd be 4/27 multiplied by 3. So 12/27. So we would have had 2 rights and 1 left. So that's C. Another nice question. I like these. Something to think about. A person drinks many cups of tea. The first cup the person drinks is filled completely. They don't want to drink too much tea in total, so the second cup is filled with fraction alpha of the first cup. Third cup, same fraction as the second cup. Okay, so we're doing geometric series with alpha being the ratio. What is the maximum value of alpha so a person may drink no more than 3 times the amount of tea in the first cup, however many drinks they take? So if we're measuring it in terms of first cups, we're going to 1 to, yeah, well we're multiplying by alpha, 1/alpha. We're doing a fraction alpha. So there we go, 1/alpha, etc. on all of these. Is that right? Oh, except alpha is the fraction. So we're doing 1, then alpha squared. Right, yeah, okay, a fraction alpha. So we're not doing 1/alpha, we're doing that. So we're getting that sum to infinity is A, which is 1 cup, over 1 minus alpha. And what do we want? That to be no more than 3. So that has got to be equal to 3. So we'll have the alpha is 2. Is that right? What am I doing? Oh no, 2/3. Right, let's multiply this out. 1 is equal to 3 minus 3 alpha. 2 is equal to 3 alpha. So alpha is equal to 2/3. Right, okay, nearly got into a mess there. Yeah, the key, yeah, is understanding what it means by fraction alpha. I was nearly doing a 1/alpha, but the alpha is the fraction. So yeah, he's getting it the right way around. I suppose that would show up if we had worked it out. If we had put it in as being 1/alpha, we would have had 1/1 minus 1/alpha is equal to 3. And then you'd get 1 is equal to 3 minus 3/alpha. And you'd end up getting it the other way up then, wouldn't you? I think our result, we'd have that 3/alpha equals 2. And then alpha is 3/2. And you'd see that doesn't fit. And then realise what they mean and come back and get C. So yeah, sometimes it's just the way of things, not quite picking up straight away what they mean in the question. A stationary wave is set up on a string of length L if the center and the ends of the string are held fixed. So we've got these fixed points, string of length L, so that is our L. What wavelengths can this stationary wave have? So m is some positive non-zero integer. So we're going to get, so our first one is going to be that. Then what we're going to have, we're going to have it going in a different direction through the middle. So we can have it doing that. Is that right? Have I drawn that right? I think I have. So that, how many wavelengths is that? That's 2, isn't it? So we've gone 1, then we've gone 2. And then the next one would be, so we want to go back to it going through that way, which means we've got to do that. We're going to connect it up. So how many is that in wavelengths? 1, 2, 3. So we're just going up 1 each time. So what am I trying to do? I'm trying to say what wavelengths can we have in all of this? We're just saying that we're going to add m is any number of any integer. So the wavelength, oh, that's the number of things. So we're going from, that is wavelength of L, that is wavelength of L/2, that is wavelength of L/3. So we're going up in ones. So that's B. Yeah, that's fine. Yeah, I find it easier with these standing waves, just thinking of what is the change in direction. You have to keep flipping. If you're going through the middle bit, we do one bit going that way, then we got it to going that way, then we got it going back that way again. So, or you could flip the ends, I suppose. That's another thing that you can try and do. But I just find that a little bit more confusing because you can end up drawing the same thing twice. Because remember, these are like envelopes, aren't they? So, yeah. Anyway, that's drawing out those. It's just more or less how many different curves can you fit in the same set of restrictions. So, question 7, a car of mass m travelling along a straight and narrow road at speed u. So m, u. The cat walks into the road, a two-legged cat, and that is at distance d. Stops in the middle of the road. What constant force must be applied to the car so it does not hit the cat? The road is too narrow for the car to drive past the cat. Yeah, fair enough. So we need to get our work done is the force times the distance. So that is going to be we want a negative force because the work done is a half mu squared. So we need to divide by d. That's going to be minus fd. So f is going to be minus mu squared over 2d. Do we have that somewhere? Oh, it's the first one. Yep, that's good. This is all ticking along fine. What is the value of x for which y has a minimum in this function? Right, so it's a positive quadratic and the minimum is going to be halfway between the roots, which is halfway between 3 and minus 1. So it's going to be at 1, which is a. Because, yeah, you always get that with quadratics, isn't there? If we got that, well, that must be where the minimum is. We've got minus 1 and 3, so that's got to be at 1. So that was a pretty easy one. What is the equation of the line which intersects that at right angles at position x equals 1? Right, okay, so the normal to this is going to be gradient of the normal is going to be minus a half. So we need to go through that. When x is 1, y is going to be 0. Oh, that's easy then. So we just got y is equal to minus a half x minus 1, which is, well, I've not written them in, oh, it's b. Yeah, minus x over 2 plus a half. Right, okay. Yeah, they just haven't quite written it in the same format. For which range of x is that inequality satisfied? Right, factorise. Looks like they're pushing us to ones. What have we got? 1 minus 1 minus 1 plus 1. So, yeah, so we've got x minus 1 is a root, which is going to leave us with an x squared and a minus 1. And, oh, that is it. So squared greater than or equal to 0. So we've got x minus 1 times x minus 1 times x plus 1 greater than 0, greater than or equal to 0. So we've got a positive cubic with a double root at 1 and another root at minus 1. So we just need, what do we want? Greater than or equal to 0. So it's anything greater than minus 1, greater than or equal to minus 1. So that is E. All right, this is good. How many more are they going to give us? Oh, it's still going. Rectangular building with sides 50 meters and 100 meters long. Flat roof on top of it. The roof has a mass per unit area of 100 kilograms per meter squared. Walls are 10 centimeters thick and contain a maximum stress which depends on the material of the wall. Right, so what materials can we use? Right, so what's the mass of the roof going to be? So the roof is going to be equal to, so we've got 50 times 100 times 100. That's our kilograms. So that's 5 times 10 to the 5 kilograms, which is 5 times 10 to the 6 newtons. That's our weight. The wall area, so what was it saying it was? 10 centimeters thick. Right, I wonder what they're doing with overlap on these walls. Right, let's see let's ignore that for the moment, because I'm wondering if you've got 50 and 100, well, what are you doing? Is that inside or is it outside? Well, let's not worry about that now. The perimeter is 300 meters. So we're going to have 300 multiplied by 0.1. So we've got 30 meters squared. And I've given it millimeters. Millimeters squared. Right, so that's going to be multiplied by 10 to the 6. So that's 3 times 10 to the 7 millimeters squared. So our stress, which is our force over area, which we can see from the units anyway, is 5 times 10 to the 6 divided by 3 times 10 to the 7, which is 5 over 3 times 10 to the minus 1. So that's around about 0.17 newtons per millimeter squared, which is tiny compared to all of this stuff. I mean, the lowest one, brick is the lowest one? Really? Brick is less, can take less stress than cardboard. Really? Oh, I don't know. That's a bit weird. And moist wood. I mean, you'd have thought, okay, concrete, I get it, but bricks, surely I'd rather have a house made out of bricks than cardboard. However, I mean, how solid are they making that cardboard? Well, I don't know if they got a typo there or if I'm just underestimating the value of cardboard in my life. But either way, we can use anything on this. So any of the materials, because they're all way above this. It does make me wonder if they've done a typo in this question, because that's a very strange answer. But I'm not going to go off and check all of those. Anyway, that's that one done. So yeah, are we done with multiple choice yet? Oh no, we've got another one. Right, okay, and then we stop. So yeah, one more to go here. Light ray passes through an infinite stack of thin transparent plates. The refractive index of these plates increases slightly by a constant factor from one plate to the next. The ray enters the first plate at an angle theta 0 with a surface normal. The ray's angle to the normal changes at each interface. Yeah, it will do. It's going to keep refracting towards the normal. So the ith interface between the plates makes an angle theta I to the normal. What's the limiting value? Well, it's just going to keep going towards the normal, so it's going to end up at nothing. Because yeah, we're coming in, we've got all of these layers, we're coming in at some angle, and then we're getting closer to the normal, closer to the normal, closer to the normal. Okay, I've drawn that in, getting very quickly round to being 0 angle, but yeah, we're just refracting down till it's going straight through. So it's going to go towards 0. So that is C. So that was a nice one to finish. Yeah, again, I don't think these are as easy as the ones we had in the 2017 paper, but they're probably going to be backloading this paper in the way they did the last one, because they weren't too bad, really, those 12 questions. I suppose the units one was a bit fiddly, and maybe the standing waves one. But otherwise, I'd say they were fairly straightforward. That was a nice batch to get you going. I suppose it settles you into a paper, doesn't it?